Essay 5.8 Turning and Inflection Points. With today's video, we're going to discuss the turning and inflection points. So section A, turning and inflection points. So turning points here in calculus refers to the maximum or the minimum point. And inflection points are very similar to the turning points. However, to be an inflection point, you need to meet two requirements. But simply, first, we can say the inflection points refers to the case where we have graph that looks like this, okay, and have a point where graph is turning, or the graph that a point that's right at the middle of the where the graph is changing its concavity. So if you look at this example, you have the concavity change. So we have concave down here and concave up. So inflection points refers to the case where there's a concavity change, and this point here is referred as inflection points. So as it has been mentioned on a couple of occasions, a maximum or minimum point on the curve is the point which has a flat horizontal tangent. So in general, if we say there is a maximum point with this graph here, so this is our maximum graph, and this point can meet the tangent line that has the slope of the zero. So this is the tangent line with the slope equals to 0. So to identify the turning points, we can set first derivative equals to 0 and solve for the x, where it can be a x point or the x point of the maximum or minimum points. Okay, so if we find the first derivative of function and if we set that equal to 0, we can find the turning point. So here we have example number 1, where we need to find the turning point of the f of x equals to 3x squared minus 12x plus 4. Since we have studied function already, we already know that this is a concave up graph, right? Or we can say that this function can have a minimum point. However, the purpose of this question is just finding the coordinate. So what we need to do first is finding the first derivative of this function. So we have to do 3x minus 12. And since this the first derivative can meet the tangent line that has a slope equal to 0, we can set 6x minus 12 equals to 0 to find that unknown x value, right? Then we can say 6x equals 12, x equals 2. So this is your x coordinate of your turning point. Then we can substitute this back into the function f of x. So we can do f of 2. We are substituting this. So f of 2 equals 2 squared minus 12 times 2 plus 4, and which is equals to 8, negative 8. So we can say that the turning point has the coordinate of 2, negative 8. Okay, then let's try to find the stationary point. So stationary points are also referring to the turning points. So you can assume that turning point and stationary points are similar. However, we're going to talk a little bit more about the stationary points a little bit later. However, so since we need to find the stationary points, then you can just say that, okay, this is the turning points. We need to find the turning points for this case. So we can say we have to find the first derivative of this function y in terms of x. So we get 3x squared minus 6x. And after that, we need to set 3x squared minus 6x equals to 0. Then this is same as 3x times x minus 2 equals 0. So x value is equal to 0 or x is equal to 2. Then we need to find the corresponding y values, right? So what you need to do is we need to substitute these values back into the original equation, y equals x cubed minus 3x squared plus 4. So when x value is equal to 0, we get y value equals to 4. And when x value is equal to 2, we get 2 to power of 3 minus 3, 2 squared plus 4, and this value is equals to 0. So we get the stationary points of 0, 4 or 2, 0. Okay, then now let's talk about how to test these turning points to see whether it is a maximum or minimum value. So if we look at the minimum shown in this diagram here, so we have minimum points here. So we can see that the curve goes from the negative slope, so negative slope, to the flat, to the positive slope, right? So in other words, the slope is increasing around this point, and which also means that the rate of the change of the gradient is positive. So in that case, we can say that when we have second derivative of the function f of x, and if it's greater than 0, we can say we have a minimum point. If the second derivative of function f of x is less than 0, we have a maximum point. Okay, so this is something that you need to remember because it's not in your formula booklet. So let's look at example 3. So we need to show that vertex of the f of x is 3x squared minus 12x plus 8, and if it is the maximum point, right? Then we need to first identify whether this is a turning point, right? Whether it has a turning point. So we first going to find the first derivative of this function. So first derivative of this function is same as 6x minus 12, and we know that if we set this equal to 0, we can identify the x value. That means we can also identify the y value by substituting the x equals 2 into the original function. So we get 3 times 2 squared minus 12 times 2 plus 8. Then we get minus 4. So we can say, okay, so we have turning point 2, negative 4. But now we need to figure out whether this is a maximum point or minimum point, right? So we're going to find the second derivative of this function. So we get 6. And you can see that 6 is greater than 0. So that means we have a minimum point. So the vertex of the function f of x 2, negative 4 is not a maximum point, right? Then example number 4, we need to find the and classify stationary points of the g of x equals 2x minus squared times x plus 2. You can solve this either using the product rule, or you can just expand everything and simplify. Okay, for me, I'm going to use the product rule. So we're going to first set the first part of the function as u, second part of the function as v. Then we need to use the product rule, we need to find the derivative of the u, right? So since u is equal to 2x minus 2 squared, du over dx is same as 2 times 2x minus 2 times, we use the chain rule. That means we need to inside again, so it becomes 2. So the final form of the du over dx is 4 times 2x minus 2. Then also v is x plus 2. So du over dx is same as 1. Then using the product rule, first derivative of the function g of x is same as u times v prime plus u prime times b. So g prime of x is same as 2x minus 2 squared times 1 plus 4 times 2x minus 2 times x plus 2. Then it gets simplified into 12x squared minus 12. As I told you before, if you want to do this question before me explaining it, you must pause the video, try the question, and watch it again. Okay? Then we can set this equal to 0 and solve for the x value. So x squared is equal to 1. Then we can say that x value is equal to plus minus 1. Then we can find the y values, right? So when x value is equal to 1, we can substitute this value back into the original equation, right? Then we get y value equals to 0. And also, when x value is equal to negative 1, we get y value equals to 16. So we can say that we have coordinates of 1, 0 or negative 1, 16. Now we need to figure out whether these are the minimum or maximum value, right? So to figure that out, we need to find the second derivative. So the second derivative of the function g of x is same as 24x, right? Then when x value is equal to 1, we get second derivative of 24. When x value is equal to negative 1, we get second derivative value of the negative 24. So we can say that since second derivative of the function g of x is equal to 24, we can say that when we have x equals 1, we have a minimum point. And also, in the second case where the second derivative of the function g of x is negative 24, in this case we have a maximum. So when we have x value equals to negative 1, we have a maximum point. So we can say 1, 0 is minimum point and negative 1, 16 is the maximum point. Okay, so now we have seen the ways of calculating the minimum and maximum points. So one very useful application of these turning points is to optimize a real-world function, such as the minimizing the cost, maximizing an area, or maximizing profits, and etc. So if you look at example number 5, we have a case of box, right? So let's draw a box. So we have box here, and it has a side of x, 2x, 18 minus 3x, and we need to find the x value that minimizes the volume. So you can see that here we need to calculate, or we need to come up with a function for the volume first, right? To find that x value. So we know that the volume of a box is same as x times 2x times 18 minus 3x. So this is same as 36x squared minus 6x cubed. Then, since we need to find the x value of the minimum point, we first have to find the first derivative of the function v. So this becomes 72x minus 18x squared. Then we can set this equals to 0. Then we need to solve for the x. So this becomes 18x times 4 minus x equals 0, means the x value is either 0 or 4, right? However, we know right away that x cannot be equal to 0. As such, there is no such thing as the 0 side lengths, right? So only 4 is your coordinate. Then we can also double check whether this x value is that minimized volume by identifying whether it is a x value of the minimum point, okay? So we can also double check whether this x point is the point that minimizes the volume by checking whether this is a minimum point or maximum point, right? So to do that, we first have to find the second derivative of the function b of x. So second derivative of function b of x is same as 36x, right? Then we can say that, okay, then when x value is equal to 4, 36 times 4 is happening, so the answer is 144. So this is a greater than 0. This value is greater than 0. So we have a minimum point. So we have proven that the 4 is the actually x value of the minimum point. So we can say that the x value equals 4 is the point that minimizes the volume. Okay, then let's talk about inflection points. So we already know that inflection point is simply where there is a change in concavity from up to down or down to up. And if the second derivative is changing sign, then that is the point where we have the second derivative equals to 0. And inflection can also be stationary point. Also, there are rare cases where you get second derivative equal to 0, but there is change in concavity. So this is not an inflection point. And so what you need to remember is to have inflection points, we need to have the second derivative value, okay? And we also need a concavity change. If the point meets both of these criteria, then we can say that is a inflection point. Okay, so if you look at this diagram, I have inflection point here because we have a concavity change. So here we have a concave down and concave up. Okay, that's the reason why we can say this is a inflection point. Okay, then let's try example number 7. So we need to verify that 1, 2 is an inflection point of the f of x equals x cubed minus 3x squared plus 4, right? So let's try to solve these questions, or let's try to identify all those turning points of this function, okay? So to do that, I'm going to find the first derivative. So the first derivative of this function f of x is same as 3x squared minus 6x. And if I set this equal to 0, I can find, or we can find the turning points, right? So we have x minus 2 equals 0. Then we can say x value is equal to 0 or x value is equal to 2. Okay? Then, since we need to verify that 1, 2 is inflection point, it is pretty clear that here with these turning points, when x value is equal to 1, x equals 0 is happening on the left hand side, and x equals 2 is happening on the right hand side. And what we need to do is, from here, is we need to figure out whether x equals 0 is minimum or maximum point, and x equals 2 is minimum or maximum point to figure out whether this has concavity change. Okay, then to figure out whether these are the minimum or maximum, we need to find the second derivative of the function f of x, right? 6x minus 6 as our second derivative. Then we know that when x value is equal to 0, our second derivative is same as negative 6. When x value is 2, our second derivative is same as 12 minus 6, which is 6. So negative 6 means it is less than 0, so means it's a maximum point. And positive 6 means it's greater than 0, so it is a minimum point. So we can say when we have x equals 2, we have a minimum point. When we have x equals 0, we have a maximum point. Means we have maximum and minimum here, right? So there is a concavity change. So we have verified that 1, 2 is an inflection point. So example number 8, we need to show that a quadratic has no inflection point, right? So we know that quadratics is in the form of f of x equals ax squared plus bx plus c, and a value is not equal to 0. That's the form of the quadratics. So means the first derivative of the quadratic is same as 2ax plus b, okay? And the second derivative of quadratic is same as 2a. So since a cannot be equal to 0 because it will be a linear, then we know that second derivative of function f of x also cannot be 0. Then since second derivative of the f of x cannot be equal to 0, then that is the only reason why the parabola has only shape of the concave up or concave down.